Okay, so welcome to the gases unit. So before we get into a lot of the gas law theories, and there's several of them, this lesson is just going to do a really brief intro of gases. So of course, states of matter, solids, liquids, and gases. Um, the state, we're now going to start talking about the forces, and it's the forces that causes a substance to be a certain state, and it's the forces between the particles that causes that. So if you have really strong forces, then you're most likely going to be a solid. And then if you have weaker forces holding you together, then you're going to have more flexibility and be able to flow, and that will cause you to cause the substance to be a liquid or a gas. Not only is it the forces that have an effect on that, so the forces, the state of a substance depends on forces. The size of the substance also helps determine the state of a substance. So the smaller nonpolar molecules are more likely to be gases, whereas your larger ones tend to be liquids or solids. So what makes a solid a solid? And this goes back to elementary science. Tightly packed particles, of course, you have that crystal lattice structure, a definite shape and volume, and limited or no movement of the particles themselves. And of course, it's affected by gravity. Whereas liquids, the particles are not as tightly packed together. So they do have some movement, and that's why they can take the shape of their container. Um, the particles, remember, all particles are in motion. So in a solid, they're going to vibrate, and in a liquid, you have that vibrational and rotational energy, which is what allows them to move around. Now, if we look at gases, on the other hand, this is where you have the vibrational energy, you have the rotational energy, and you have translational energy. And this allows gases to move freely in all directions, and therefore is not affected by gravity. Gases will not fall to the ground if you drop them like a solid or a liquid. And the particles are very independent of each other. So if you look, this is, we're talking about that translational energy. They can move around throughout a container and freely. So of course, uses of gases, this is something that, just as a by note, so heating our homes, of course, scuba diving, and breathing. Okay, in itself, these are all uses of gases. Being able to breathe, the actual act of breathing, is very interesting in itself. If you take biology, or if you are going to take biology, you will discover that. So with the kinetic molecular theory, there are different assumptions that we make, and we of course make the assumption that gases are tiny particles, but we're not talking about just tiny. We're talking about being so small that the volume is actually like there's nothing. There's no volume. Um, and these particles are in constant random motion, and they collide with the walls of the container. And it's that causes the pressure from the gas. It's those collisions with the side of the container. And we just assume that they do not attract or repel each other. Um, the other assumptions, of course, is that these collisions are perfectly elastic, so you have no loss of kinetic energy as these collisions are happening. And so you have this kinetic energy of gas molecule is directly related to temperature. So as the temperature increases, the greater average motion, and the greater average kinetic, you have a greater average kinetic energy. Now, the thing is, this is a hypothetical, ideal situation, and we know that actually isn't true. But a lot of what we will be dealing with within this unit are ideal gases, which isn't really reality. But the reason why we do this is so that you get an understanding of what gases should behave like and do normally do behave like, but there's other factors, of course, that affect that. So an ideal gas takes up hardly any space, and the particles do not attract each other. And you know that while would be nice if that were the case. That's not necessarily true. So we will be focusing on gases in closed systems. And if you have a closed system, you're not losing anything. Some of the particles aren't floating off into the air somewhere else. So you have that constant moles of a substance. So it's not open to the atmosphere. And so these are gases that's contained within something like fire extinguishers or oxygen tanks. Now, if you have a closed system, then you can actually look at the factors that affect gases in this ideal situation. You have temperature, pressure, and volume, and this is where we are going to have a lot of our focus throughout this unit. So when we talk about pressure, and we will talk, like I said, about temperature and volume as well, all separately and then all together. Pressure is force exerted upon surface area. So this is where you get that um, P equals F over A. So pressure is force per surface area. And there are several units that we use for pressure depending, and you are going to have to be able to do the conversions for any of these. So pascals, kilopascals, atmosphere torrs, and millimeters of mercury. And I'll give you those conversion factors for you to use. So basically, with the pressure of a gas, it's not the same as the pressure of a solid or a liquid, and we can't measure it because really what we're doing, we're trying to determine the kinetic motion of molecules. Um, so if you fill a basketball with air, like in the example here, the more molecules collide with the inside of the basketball, and if you have more collisions, and that increases, and there's a stronger force in those collisions, then that gives you your gas pressure. So if you look at, if as you add more and more gas molecules in here, there's going to be much more going on, and you get that net force or pressure on the container. Now, there's several ways to measure pressure, and one way, of course, is the barometer, whether you're familiar with that or not. Um, the thing that I want you to note is that a barometer measures absolute pressure. So this is the actual pressure exerted by a gas. And this, of course, was first made by this handsome gentleman right here. And basically, his idea was that you have this barometer, you have downward pressure caused by the weight of the mercury in the tube, and that tries to force the liquid out. And then you have the air pressure, which is forcing the liquid to stay there and pushing mercury up in the tube. And depending on where that mercury moves, depending on air pressure, that measurement is what gives us that pressure. This one looks a little bit different. It shows, when I said millimeters of mercury, that's literally what you're measuring, how many millimeters the mercury moves through the tube. Okay, so the mercury falls under pressure exerted by its weight, and that equals the atmospheric pressure. And then as those two change, then you get the barometer moving, the mercury moving in the tube. A barometer actually looks more like this, and this actually should say mercury. So water is less dense than mercury, and the atmospheric pressure of 76 centimeters of mercury would be equivalent to 1,034 centimeters of water. So we use mercury because it doesn't move a whole lot, um, because it is more dense, and so that minimal movement is easier to measure. You can also measure with a manometer, and as the barometer measures um, absolute pressure, a manometer measures relative pressure. So this is the pressure exerted by the gas relative to the atmospheric pressure. So I was talking about the conversions. Here they are. and this is something that you're going to have to know and be using a lot over the next week or so, couple of weeks. So basically, the column of air above 1 square meter at sea level. So you have the Earth. There's our North America, South America, and that looks really bad in Europe and whatever. Um, 1 meter squared at sea level, that column of air, okay? Um, and if you have 0 degrees Celsius, is 101.3 kilopascals, okay? So that is the standard atmospheric pressure. So this is a number that you're going to have to remember. And basically, standard atmospheric pressure, 101.3, is equivalent to, so 1 atm is equal to 760 millimeters of mercury, and 1 millimeter of mercury is equal to 1 torr, and 1 atm is equal to 760 torr. So basically, what all that means is all of these are equal. 101.3 kilopascals is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 1 atm. And to convert, of course, you're just using ratios. So if you have 100 kilopascals, you want to get rid of the kilopascals and you want to change it to torrs. Okay, so there's 760 torrs for every 101.3 kilopascals. Cross those out, do the multiplication, and you get your answer. So that's your brief intro. Make sure you write down these conversions, and because you're going to be using them throughout this whole unit. And next we move on to starting the different laws.